Yeah, so let me go ahead and get started here. Welcome everybody to our Neuromaker STEM webinar on assistive technology. So today we're going to be talking about a few different pieces of assistive technology that we've worked in here in the lab, and how we've taken some of those experiences and made them accessible to students. And I will also throw out there, I'm going to make more than one reminder in case some people come in here late. We have two very special secret guests. They're not going to be so secret because I'm going to tell you who they are in just a moment. But we're going to actually have, once I get through kind of the presentation part of this, which I'm going to keep at a minimum, two actual biomedical engineers, one of which worked on our actual prosthetic, and specifically on a lot of the AI algorithms and firmware that went into that. So if you have any questions that come up over the course of this webinar that relate to how an actual biomedical prosthetic ends up in people's actual practices, then you will have the right people to talk to at the end of this. So keep your questions handy. We'll get ready for bringing on those special guests at about the 20-25 minute mark of this presentation. Then we'll also have a second engineer who is our highly esteemed senior product manager, Kyle Lee, who is tasked with taking all those amazing biomedical experiences and translating those into something that students can experience. So I think whether you are interested in the actual technology behind this biomedical science, or you're interested in how that technology can work in the classroom, we have both your bases covered. So all I'm going to do ahead of time is just give you some of the basic facts about how we went through that process, how we have that experience accessible to students that work with us. You'll have a whole lot of content that you can leave away with here, investigate on your own as well. And then we'll wrap this up by actually opening up questions. And I'd love to make this as interactive as possible. If anybody wants to be promoted to a panelist, so you can turn your camera on and ask questions or anything else, we'll absolutely make time for that. And I'd love to make that the real focus of what we work on here today. So let's go ahead and get started. I'm going to go through some introductory pieces here, just so we all start at the same level. And then we'll actually have some engineers to work with us later on. So while I'm getting this all set up, I love not talking into the dark, cruel void of Zoom, as I imagine many other teachers here have done as well. So feel free to drop in some comments, questions. One thing I would love to start off with is, wherever you are from, feel free to drop in the comments there of where you're repping. We want some representation across all over the place. I'm personally repping Milwaukee. I grew up in Massachusetts, lived there for a long time, and I just moved to Milwaukee about 3 months ago, and I'm having the time of my life. I actually live next to a bowling alley here, which is probably the most Wisconsin experience possible. And I can make that the subject of a future webinar if you would like to know. All right, we got some Idaho repping. We got Colorado. All right, where else we got? We got California, we got Washington. All right, we're repping everywhere, we're repping, good. All right, so let's get started. Who are we? Who is this guy talking to you from some random place in America that is indistinguishable from his background? Well, I'm coming to you from Brainco's Neuromaker division. So in case you're not familiar with us, Brainco was incubated in the Harvard iLab about 6-7 years ago. We're one of the top 10 brain-machine interface companies in the world. By head count, we actually might be the largest BCI company in the entire world. And we have lots of cool stuff. You can actually take these pieces away in our blog if you want to learn more about the specific details. We feature some technology from MIT and NASA. Actually, a lot of the algorithms that power our BCI applications are based off of NASA research. We're actually featured on the NASA website. If you want to take a look at that, on some other engagement pieces, which are super fun and cool to look at. And we've also been heavily involved in the world of education technology. So we're all familiar with ISTE. We've gotten all kinds of collaboration with them, and you'll see us at all kinds of different booths and stuff like that, that hopefully come back to normal at some point once this COVID stuff starts to die down. And who is this guy talking to you with maybe decent hair? I tried to make it up a little bit today, but you know, what can you do? So I am a former, I actually started off my career as an ESL teacher in China. And from there, I've done STEM education, all kinds of different stuff. And I've really spent the past 11 years doing all kinds of international STEM programs. If you're familiar with First Robotics, I managed that program in China for about 5 years. I was one of the founding group members of First Global, which brought STEM education programs to 183 countries around the world. We couldn't quite get North Korea on board, but if somebody else can help make that arrangement, I'd love to get a couple more countries involved. I have my master's in technology, innovation, and education from Harvard, and I am a product manager here at Neuromaker. And I have one of the coolest jobs in the world, which is working with people way smarter than me and trying to figure out how we can make their experiences accessible to students and educators all over the world. So that's a little bit about me. And more importantly, what are we going to talk about today? Well, if you saw on our webinar page, I do want to spend quite a bit of time talking about things like the protocols that biomedical engineers use to make a prosthetic and some of the design thinking frameworks that we use from the lab side of things and how that correlates into some student-centric activities. I'm going to open up the hood on some of our projects and activities that go into this a little bit more. So you will certainly be able to see some of that. Also, I'd love to spend a little bit of time on how we can design and create materials to wear and test a model prosthetic. So if anybody out there is actually using one of our Neuromaker hands, we have all those materials available in our web portal, which I'm going to open up the hood on as well. Also, one of the questions that I'm probably going to leave to our special guests are some of the design choices that you can make to improve the quality of life from those who need assistive technology. And for those who might be unfamiliar with this term, assistive technology is just a fun word that we use to describe any kind of technology that helps people who need a higher quality of life. So whether you're doing a prosthetic arm, or you're doing some kind of new wheelchair technology, or really anything. So we've seen projects for people that work with pets that need some sort of special assistance, people who need to have better hand-eye coordination if they have some kind of ocular issues, really anything. It's a very broad science, and there's a lot of cool research and projects going on in this space. So I'm just going to start this off by talking a little bit about some of those design thinking frameworks and what we do with our solution. And then I'm going to bring in our special guests who will talk a little bit more about how this stuff works in the lab, and hopefully some takeaways that you can take so that you can help replicate these experiences with your students in the classroom. So let's go ahead and get started. So as some of you might be aware, here's kind of the endpoint, or at least the floating endpoint for a lot of our technology. This is the brain robotics prosthetic. And if you are new to our community, this prosthetic actually fits onto the residual limb of an amputee. So say you're missing your hand at some point below the wrist, and you need to have like a model hand to replicate the motions of a natural human hand. Well, you can put on this special kind of prosthetic, and you'll see on this black portion behind the hand, this is a customized socket that goes on, that has to be made specifically for an amputee, depending on where the residual limb ends. And on the inside, what you can't see, are special sensors called EMG sensors, which detect muscle signals in that residual limb. So that, you know, if I'm missing my arm right here, then we'll have some sensors on the upper part of my forearm, and those will actually measure the electrical activity coming from your arm. And what's really cool about this is you can actually tailor the signals from those sensors and be able to control the movement of your hand here. So as you can see, one of our, actually the amputee who's demoing this technology is an absolute incredible person. He runs ultra marathons all over the world and will absolutely school you in any kind of physical activity you can imagine. And he is demonstrating how after a little bit of rehabilitation that comes along with this kind of prosthetic, how you can actually move a prosthetic hand very similar to the movements of an actual hand. So this is one of the coolest applications you can see of AI. So like all these complicated muscle signals coming from a residual limb go through special AI algorithms, which are classifying what kind of movements an amputee wants to make based on the signals that come from that muscle. And then those will ultimately be replicated into a number of different gestures. So this is really the experience that our engineers have created in the lab. And our whole job is, how do we take the fundamentals that came from this experience and some of the tech and make it available to people who want to investigate this in a bit more detail, not just the technology side of things, but even the empathetic part, right? So how do we really know what issues we want to solve with an amputee, what things really matter to them, and what's ultimately going to make their quality of life better. So how do we do that? Well, this might be familiar to a lot of you out there who are using design thinking frameworks. Exactly what is going to, exactly what happens in the lab is the same that we do with our educational materials. And I see that some questions are coming in here. I'm going to go off on a tangent, all kinds of stuff with our presentation. And we actually have a couple of partners in the chat who can answer things live. But if your question does not get answered immediately, I'll definitely get to that once we get through some of these initial portions. Where do we start with this whole process? Well, you might be familiar with this if you're doing any kind of project-based learning in the classroom. This is the exact same process that happens in the lab that you might be familiar with in the classroom. So design thinking is all about going through these 5 steps that allow ideas to be turned into actual products and things that we can use to fit some sort of a solution that is wrapped inside of some kind of a problem. So it goes with empathizing with the problem, defining what the problem is, ideating solutions to the problem, using a prototype to test the solutions, and then finally, you're gonna see that test word a lot, testing and testing and testing until you can make some tangible progress on the problem that you wanna solve. So I'm just gonna go through a very quick description of what each step of that looks like, and then we're gonna talk about how that actually went into our prosthetic hand and some other ways that you can get involved with an educational set. So let's go ahead from the start. So empathizing. So this is hands down the part of the process that is heavily overlooked by a lot of the engineers that get set to solving a particular problem. If anybody out there is familiar with the terrible concept known as solutionism, there is no greater depth that somebody will sink into when they create some kind of technology, which is we want to solve problems. We don't want to create solutions that look for a problem. And that all starts, number one, with empathy. So when we have, whether it's our scientists in the lab or it's students out in the classroom who are thinking about their solutions, step number one is empathizing as much as possible with the people that you want to help or the problem that you want to solve. So you'll see here, this is actually from the amputeecoalition.org. They're an amazing nonprofit that helps awareness and all kinds of benefit programs for those that have limb differences. And they have amazing resources on some of the empathy aspects that get overlooked by a lot of prosthetics out there. So on this piece of thing, we'd like to challenge our students and the people in our laboratory to really work with amputees as much as possible. Actually, what we start off with in a lot of our classroom activities is going through a full class without the use of one of your arms so that students can really figure out what those actual steps are that are difficult for an amputee as opposed to somebody with 2 hands. So things are as simple as, like putting your hand in a glove and then going about the course of your regular day, trying to tie your shoes, take a shower, whatever it may be. You'll notice that there's specific pieces of the day that are much more difficult for an amputee that might not be obvious at first. So these are ultimately the problems that we identify and try to solve. And then you can go into actual ideation and testing. So this is heavily overlooked and hands down one of the first steps that we want to get to. So once we figure out the empathy part of things, we move to our definition side. So here's an exercise that we work with a lot with the students, which is simply creating a problem statement, right? So you want to define exactly the problem that you want to solve. You don't want to go on a wild goose chase making technology that's ultimately not going to go anywhere. So a very simple way to do that is just by starting off with a statement like this, and just filling in the blanks. Somebody might need a way to something because of something, right? So in this case, a lower arm amputee might need a way to pick up and use a fork because that person needs to live independently. So this is the same process that we do here in the laboratory, and this ultimately translates into what we do with the students too. So I know some of you out there who might want to jump straight into the coding or programming or building. I heavily recommend that people start off with creating a simple statement like this so that they can focus their efforts around an actual problem. And of course, this is something that gets revisited and reiterated after plenty of time goes by. So from there, once you have your problem statement, then it's all about ideation, right? So what kind of ideas can we make that are going to fit the premise of that problem statement? So There are people out there way smarter than I am, one of which is Bill Burnett of MIT Sloan School of Management. So he says a team should silently vote for these ideas based on the following criteria. So first, everybody creates all kinds of ideas. I'm sure that your approaches in the classroom are going to be better than mine, but anybody is welcome to post something that they think will help. And then you ultimately try to get to this kind of a combination so that you can get 4 ideas based on their potential, not their feasibility, 2 ideas most likely to succeed, 2 ideas that are most likely to delight users, and 2 ideas that are the most breakthrough. So from there, you can take a huge thought bubble of the things that you think might be able to solve a problem, and then really narrow down these different criteria and use those as a basis for testing. So these are some simple kind of thought exercises that we have our students go through. And this ultimately gives people the right framework where you're not just looking for something that's the classiest or the most technically advanced. You're really honing in on different aspects of how the solution can be integrated. So those are some of the ideation frameworks that you can use. And these are a lot of fun to do in the classroom. So people really get to go outside of their realm of comfort and start to come up with ideas that they're not afraid to entertain. So people know that a lot of these are going to get shot down, but ultimately we all get to the right place. So once you have your problem statement and some ideas to go through there, then it's time to create some prototypes. So there's lots of different prototypes that can happen along the ideation stage. However, the important part of this is you want something that's quick and simple and something that you know can change. So Tom Schur of Google Glass has 3 big rules. They certainly had to do a lot of ideating for Google Glass. So you can imagine that Tom had quite a bit of experience to wrap this around a few different axles. So number 1, what's the quickest path to your experience, right? So what can you build very quickly that's going to be able to give you tangible feedback on whatever your idea is? Number 2, doing is your best kind of thinking. So instead of spending a lot of time on paper thinking about how something should be, you're going to get to a destination a lot faster if you have something that you can actually work on and test. So you can even see here in the picture, this is from the University of Washington Steel Lab. So when they were putting together different prosthetics prototypes, these aren't just students, they are also engineers as well. They even use some of the low-res prototyping that you can see here so they can get to some tangible outcomes very, very quickly. So of course, you're eventually going to go into some higher level programming and design, but you absolutely want to start with something very easy to start with so that you can get some basic feedback. And that's actually one of the things that our users get to work with the Neuromaker hand, because the product that you get to work with is one of our first prototypes of our actual prosthetics. So you get to really relive this. And then number 3, use materials that move at the speed of your thought to maximize your rate of learning. So don't try to find something that's explicitly difficult to change. You want to have something that you can change quickly. So this is where you don't have to do injection molding your first time around at creating some kind of an actual piece of hardware. You can start with something that's very simple and easy to prototype, whether it's a 3D printed object, even working with simple things like clay and paper mache or whatever it may be, are great ways to start to get the ball rolling and get some ideas off the ground. Okay, and then once you have your prototype, then it goes on to the test. And once again, this is exactly what happened with our actual biomedical prosthetic. So the Stanford School of Design has 4 aspects that students need to consider with their end users, right? So what's the prototype that you're using? What's the context and scenario that your prototype is being used in? So one thing that's often heavily overlooked, even with things like prosthetics, are the environment that it's used in. So for instance, whether you're looking at FDA standards or you're thinking about what's going to happen with like an amputee's daily life, can things be submerged in water? If you're going to wear a watch or something like that, is there some way that you can add that in that's comfortable? So the scenario and the context that things are working in is very important. Number 3, what's the interaction with the user and the designer? One of the things that we found very early on with our prosthetics prototypes is that it's a lot different to test something out in the laboratory with someone as it is if you have an amputee going to an actual prosthetic clinic. You're going to need to have somebody else operating this technology and explaining it to people. And if you can't replicate that same experience with somebody who's outside of your purview, then you're going to run into a lot of issues. So knowing what that interaction is very important. And then number 4, what's the process and method that you're using to capture, observe, get feedback, and reflect? So whether you are making a bunch of spreadsheets or you're doing different diagrams that give you this kind of feedback to your engineering team, having that in place is extremely important. And actually, one of the things that we require all of our students to do when they're going through their prototypes is keeping lots and lots of feedback and notes, so that when they can revisit things again, that they'll be able to know exactly what the results are of different things, and they can make sure that they know where to put their effort. So, and of course, not everybody's going to get the chance to work with an actual amputee. So you do not necessarily need to test with a real user. And this is across the board with all of our technology. So whether we're doing different things with our brain-computer interface tech, we're not necessarily prototyping these materials on people who are actually going to use it. So I can speak from my own experience helping to design educational programs and hardware, that we actually start off with people who, I don't want to say this, the people on our team itself. So if you can get somebody else who is not yourself to get to the same outcome that you can, then you're typically moving in a good direction. So there's a lot of resources that are available to you that might not be obvious. And one of those are just the community of people around you. So don't worry if you can't test it with a real user. And this is probably the fastest introduction in the world to the design thinking frameworks, especially as they work with an actual prosthetic. So all I'd like to do now is just show you a little bit about how people working with our set can go through those things. This is not meant to be some kind of a sneaky Billy Mays product presentation to you all. I just want to show you some of the frameworks that we use, and you are more than welcome to investigate these as well. But I think these will shed some light into the process that we have our students work through, and I hope that you can replicate with your students as well. So if I click on this link, this is our 3D printing exploration, which we use to have students go through this empathetic connection with creating a prosthetic for an amputee. And where we actually, where we have students start off with a problem statement is by actually using real world biomedical engineering standards. So this SHAP protocol, this is the Southampton Hand Assessment Protocol, is what our first design of our prosthetic had to pass in order to move into a higher stage of development. So I'll just open it up so you can see it. Just so you know, the world of biomedical engineering moves fast, and there's actually a lot more procedures out there now. But this will be a great way for students to really see a real world issue that they can start to ideate and think around with something that actually happens out there in the world. So you'll see here in this documentation, this is the actual protocol that a assessor uses. So if there's whether it's a test facility or a prosthetics lab out there, like they have a new prosthetic and they want to see, hey, is this thing worth my time? Is this actually going to be able to be usable with an amputee? Well, they're going to go through these tests. So there's a bunch of boilerplate language here on how to do this, but ultimately you have to pass a test. So you have to be able to pick up and manipulate certain kind of objects like this. So whether it's picking up spheres, whether it's opening a door, whether it's manipulating some kind of a cube, these are the things that an actual biomedical engineer has to pass in order to make sure that their prosthetic can move farther. So in our particular unit, we have students work from these actual real world issues. And what you can see from our materials is that I'll allow, so this link is freely available. If you actually go to our Neuromaker page, so neuromakerstem.com, take a look at our user portal. If you find our 3D printing curriculum, you'll be able to see all this stuff open to you. So I'll allow you to go through this stuff on your own. But this is ultimately what we have students investigate. So before they even start to 3D print out anything or create any of their creations, they have to empathize with their users. So we have students learn a little bit about some basic biomedical engineering concepts and empathize with the amputee community. And only then can they go on to start to take some 3D printing concepts and apply them to the use of their kit and start to think about solutions that they can make. So anyone, and it's amazing. It's absolutely amazing how overlooked that this gets, not just in the classroom, but more importantly, even out there in the world of actual engineering. The people designing certain solutions don't do enough legwork and research on what the end result they want for their user actually is. So I cannot stress how important that is. And we spend a lot of time making sure that our students understand that process as well. So only then you get to start prototyping here and then doing a design evaluation. And then, like I said, there's this revolving cycle around how you can prototype something out, test it, see how it works, and then ultimately make your own prosthetic. So by the end of our particular unit, students will actually be able to create a 3D printed hand. So I'm just going to skip ahead so you can see some of that. So they'll be able to print this out and actually test it with those design learning frameworks that we've mentioned. And there's all kinds of supplementary material. I'm not going to talk too much about that. So feel free to jump into this portal if you'd like to see more. But those are just a few basic building blocks that we've put together on the medical side of our operations that correlate with the educational side too. So those are some of the big things that I wanted to touch base on. I'm going to take a look at the chat. Oh, yes, I will certainly drop this link in the chat. Give me just one moment. So here is the direct link to this page. And then if you want to circle back and look at some of our other curriculum, you can certainly do that on our navigation bar at the top. So that's where you can see some of that stuff. Yes, apologies for the fan. I'm going to see if I can move my camera just a little bit. Unfortunately, my apartment here is pretty bare bones and I do not have great air conditioning. So that is the environment I live in. So, all right. So what I'm going to do, so Mike, I'm going to get to your question in just a bit. But while I get that set up, I'm going to open up our participants here and I am going to bring on two of our all-star engineers. So I'm inviting Amir and Kyle to our chat. So hey there, Amir. We're just going to give some time to have that mic work. So yeah, Amir, whenever your mic works, feel free to say something and then we'll be able to chat a bit. Give me 1 second. And Kyle, if you can hear me too. So you can go ahead.
Is my microphone working? Hello?
Oh, I can hear you loud and clear, Kyle. Amir.
Awesome.
Yes. So while I get Amir set up here, Kyle, could you share some of your experiences using these kind of frameworks and like how you've overcome some of these engineering challenges?
Absolutely. Hi, everybody. First of all, thank you so much for joining this amazing webinar. And thank you, Andrew, for doing all these amazing intros. So my name is Kyle. I personally work within Neuromaker and BrainCo. And when I first joined the company, I used to work with the Brain Robotics team, which is the team who produced these real prosthetic hands, just as you've seen in the video. And then later, we used one of the original prototypes from Brain Robotics and turned that into a brand new and groundbreaking education experiences. So personally, because I worked in the Brain Robotics team, I also worked with amputees and the customers. So that's, I think, is really important part of the reason why I want to kind of have all these things to influence our next generation, to let them to think that, okay, all these knowledges you're learning, they're not only to make you more technical in your work field, but also all these knowledges will actually make sense. They will help you to actually design and solve a real world problem and help those people who are truly in need. So that's something that I'm personally really proud of doing right now. I'm really proud of what we're doing as a Neuromaker team in the education vertical. So if you have any questions regarding how specifically to use a product, or if you have any other questions regarding Brain Robotics or STEM kit in general, feel free to ask me. I can answer all those questions for you.
All right, sounds good. So in a moment, we'll have Amir join us too. So Amir, when your microphone gets working, just feel free to say something real quick.
Hey, can you guys hear me?
Yes, so welcome, Amir.
Hi, thank you for having me on, Andrew. Okay, so hello everyone, my name is Amir Khan. I don't know if you guys can see me, the camera is acting a bit funny, but I work in the Brain Robotics team. I've been with BrainCo a little bit more than 3 years, and I've started as an embedded systems engineer. So I started actually working on the Focus headband, and I used to design the embedded architecture for it. And then I moved on to working onto the prosthetic hand that we have in house, on which the NeuroSTEM STEM kit is based. And yeah, as you can see in some of the demonstrations, so I used to work on the motor drivers and how to control the motors, how to make them grab an object, and I've moved on to testing a lot of the code that I write and making a modular architecture so that we can have our future generations use some of our current code. And also a lot of it goes into testing, and then we have users that we work with. So we actively try to find out that our design is optimal, and we get the kind of outcomes that we expect. And a lot of the feedback goes back into designing, and it's a whole workflow. When we design new features, we optimize it, we test it, and then it goes back to designing if it needs to be improved. So yeah, that's a little short introduction. If you guys have any questions, you guys are excited about the biomedical field, about engineering or like embedded systems in general, I'd be happy to answer any of your questions.
Sure. So I'll feed you a couple of questions here that I'm seeing, Amir, if you don't mind.
Sure.
Yeah. So one question I'm getting is, what are some of the biggest actual design? Let me see if I can read this correctly. What are some of the actual solution statements that you've had to work with yourself that have turned into some kind of a product improvement? So if I interpret that correctly, what are some of the issues that you've seen in the world of amputees, and how have some of the solutions that you've made address those?
Right, great. Yeah, that's actually a great question. I mean, over here, me at least personally, I strive to make the best of the product that I design. One of the very latest features that I worked on is motors are driving the fingers, but then how do you know whether something has grabbed an object, and how do you know whether the object is like a hard object or a soft object, and like what kind of force do you really grab the object with, and when do the fingers realize that it has touched something and it should stop moving, and not like force in so that it doesn't crush that object. So that is one of the questions that I helped answer, and I designed some kind of a motor protection control embedded architecture, when the fingers are continuously monitored for any kind of resistance that they feel as soon as it comes in contact with an object. And depending on the threshold that we set for resistance, that can help us grab hard objects as well as soft objects. So I think that's one of the features I would like to highlight is grabbing an object, making the fingers like pause there, and make sure that you are actually holding onto the object for as long as you like, without really straining the user, and without the amputee having to make too much efforts to actually do simple tasks like that.
Great. So I'll keep asking you questions as they come up here. So another one, like, how does the AI actually work?
Oh, great question. So in-house, we actually have two ways of doing that. We actually have a system that is just based on 2 electrodes. We have a system that's based on 8 electrodes. To give like a better view of, I'll keep it simple to 2 electrodes, right? So we have 2 electrodes that is attached. One, I wish I could show you. I don't know if you guys can see my screen. I'm thinking not, but
oh, yep,
one is, oh, you can see me? Oh, yes. Okay. I can't see myself, but okay. So, oh, there am I. Okay. So, so we have 2 electrodes attached. One is like in the front of your forearm. One is at the back of your forearm. And the 2 kind of movements, when you move your hand in versus out, it can give different spikes on the electrodes. So our firmware is and software is designed to continuously monitor the data that comes from the sensors. And depending on whether you make a gesture to maybe, let's say, an inward movement or an outward movement, we can program the detection of those gestures to make a certain kind of movement. For example, let's say that the user wants to make, let's say, a finger pointing gesture. We call these gestures, by the way, just any kind of hand movement that they want to perceive. So let's say an amputee wants to make a finger pointing movement. So let's say that he gives we have programmed as one movement inwards to be a finger pointing gesture, and things like that. So let's say one movement inside is like a finger pointing, one movement outside is like another gesture, maybe making a rock on gesture. So depending on the different coding, or depending on the different circumstances, or like the different grips that the amputee would like to have, we've mainly put the common ones to have simple kind of codings, like, detect in, detect out, stuff like that. The way that once the hand actually goes into a gesture and they want to now move the fingers inside, in or out, it's based on the fact that they can hold the in signal, or we call it like the close signal. So as long as it's holding in, that your fingers are trying to grab something. And when the same thing is done on the other side, there's an out signal given or open signal given. So the fingers are turning back to a full open palm position. And we kind of have like training modules where we sit with the amputee, we give them like, suggested ways of training the device, just to get their muscles up and working and make sure that they get used to the system and how it's supposed to be used in an effective way. I hope that kind of answers what we're trying to do.
Cool. Yeah, I'll keep manning the chat here to make sure that if there's any follow-up questions on that, I'll let you know. So the last question that came in right here, and I'll allow anyone else to answer anything too, is like how do people become a biomedical engineer? How do you do what you do? So
I would say, so that's actually a very interesting question. I don't know if there's a direct answer, but there's actually a lot of ways you can do this. First of all, a very immediate step that you can do is follow BrainCo, Neuromaker, be a part of this, of course. That should give you a good start off point. But I joined by pursuing my master's in computer engineering, and that led to just making me designing embedded systems. And I started off by, just designing a robotic hand. And then sooner on, because of opportunities at my workplace, I got to be involved with the algorithm side of it, the control side of it, and the testing side of it, and the design part of it. So I was fortunate enough to get the opportunity by BrainCo to be involved in a much larger aspect. But there's a lot of other ways to get into it. For example, pursuing a degree in algorithms can get you here, or in fabrication of arms and limbs, prosthetic, of course, and also from a medical point of view, you can become an orthopedic. I'm sorry, I forget. A prosthetist who actually deals with patients, and they're like industry experts on what kind of system would be applicable for the different people out there, different kind of applications that people have. So that's there's a lot of different ways depending on what kind of background you are interested in and how you go about it.
sounds great. So I'm actually going to turn my camera on very briefly. There we go. So I'm not too close to the screen. Yeah, so I don't see any other questions in the chat here. I'll give another minute for anybody to ask any last minute things. But yeah, we'd love the engagement with like really being able to bring in some people from the lab. So Amir is actually coming to us directly from our lab. Yes.
Yeah, I'm in the workplace, so yeah.
Yes, so like not too far away from he is right now is where a bunch of our prototypes are and all that kind of stuff. So let me give a couple more seconds. It looks like people seem pretty satisfied with what they have so far. So yeah, so how about this? I will, so this recording will be available for anybody who wants to catch up on this or any other questions that people have. But if you want to reach out to us at all, you can find us at neuromakerstem.com and drop us a message, and we'd be happy to get back to you. So just to bring it out there, Mike, we will get back to you with one of our partnerships team to come out if you have any additional questions on the solution itself. But if anybody else wants to reach out to some of the engineers in our organization, we can certainly make some time available for that too. So like anything that we can do to kind of bring these experiences from the actual laboratory two people out there teaching it is one of the things that we enjoy the most. So with that, I will bid you all adieu. Amir, thank you so much for answering those questions. Kyle, thank you for coming on too. And I think we did a great job here, and I hope you all have a great day. So.
All right. Yep, sure. Thank you, everyone.
Sounds great.
Thank you guys.
Thank you.
All right. Yeah. Bye.